Okay, so hi everyone, welcome to CS2105 week 6. Yay! I hope you all are not dropping after this week. So this week we are going to talk about the pipeline protocols and also the TCP protocols. Especially for TCP, I think your prof covered this in quite detail, so ensure that you actually quite give the exercise more read lah. Okay? But before that, we discussed about stop and wait protocols. We have RDT 1.0 all the way to RDT 3.0. And we have discussed like each of them will introduce new features to handle like the assumptions in the environment. So in this case, all the features we already discussed last week on why the features are needed. Okay? And which I provided a bonus question last week. So here in stop and wait protocol, we assume that the packets cannot be reordered because you can only send one packet at a time, right? So it's definitely going to be one, receive, another one, receive, okay? So we assume that the packets cannot be reordered. However, stop and wait protocols provide some kind of inefficiency. You see, this was my timetable last semester. It has so many empty spaces, very inefficient. What if you actually use this for lead code and stuff, right? Okay, so this is very inefficient. How would you be a more efficient NGS student? Let me show you. This is what you call pipeline protocols. Okay, so you ensure that you want to try to improve the utilization of the host. Okay, for the server and the client, you want to kind of improve the utilization. In the case of a stop and wait protocol, right? Say you want to transmit a file, you can only wait up to this point, then you will have to wait for a propagation delay, right? But in the case of pipeline, then you can kind of like better utilize this. Okay, so the proportion of the transmission delay against the propagation delay that will be higher. Okay, that means you want to improve the utilization of the host. So pipelining protocols, the environment that we assume is actually same as RDT 3.0. That means we assume that the packet loss and bit errors may occur. Our goal here is that we want to increase the utilization of the link and also increasing the range of the sequence number sent. We will see later on. We introduced two types of pipelining protocols. The first one is a go back N, then second one is selective repeat. Okay, each of them have different styles. You can see this later. But for go back N means that you will send like all N packets at one go. Right? So N is like your window size. So sender will send N packets. But the important thing is there's this thing called a cumulative ACK. What is cumulative ACK? Okay, there is a window, there's a storage buffer, but what is the ACK? Okay, so this means that if you receive up to say packet N, then you ACK N lah. You don't have to ACK the individual items, right? Okay, so yeah, something like this. If some duplicate item come in, you just ACK the latest one, right? Okay, so if receiver receives out of order packet, the thing here is that your packet is going to be discarded. Okay, that is the key part of your go back N. So if, say for example here, you send packet 0 come, receiver will give you ACK 0. But packet 1 is lost. Then packet 2 comes in. Because packet 2 is out of order, you're going to discard this, then you will send ACK 0. Because 0 was the last in order item that you received, right? Okay, so it will still be ACK 0. Packet 3 comes ACK 0, packet 4 comes ACK 0, packet 5 comes ACK 0. So as you can see, this method is kind of inefficient also, right? Because in the case that the early ones fail, then whatever else that are successful, these are going to be discarded by your receiver. Okay, that is your go back N. Okay, so something like this. Then in this case, you will see that 0 comes in, 1 comes in, 2 comes in, but the ACK for 0 and 1 is lost. Okay, so then your ACK 3 here is also lost, thus only ACK 2 comes to the sender. In the sender's perspective, now the window will shift because ACK is cumulative, right? So ACK 2 means everything up to 2 has been received. Thus on the sender side, you can just shift the window to after 2. Okay, so 0, 1 and 2, you can skip this. You move the window to 3, 4, 5 and 6. Okay, but 3 and 4 is still being sent, right? 3 is being sent, right? So you're going to send 4, send 5, send 6. Because it doesn't know that 3 is lost yet. Okay? Up to the point where there's a timeout for packet 3, then you will have to resend this whole window. Okay? That's your go back N. Any questions thus far? This would be part of the more complicated questions in the midterm, I suppose. because of the pipelining protocols. Any questions? Doubts? No? Okay. So instead of having to discard these packets, what if we want to kind of like keep them? We keep them first, then afterwards, if any out of order packets, we can just reorder them. That is basically the goal of your selective repeat. Selective repeat, we are going to buffer out all the out of order packets, and we are going to ACK each packet individually. Okay, so in here, we are going to move the window to the last un-ACK packet, and it's important to note that the sender will keep a timer for each packet. Okay, previously for go back N, you just need to keep a timer for the last un-ACK packet. For here, you will have to keep track of a timer for each packet. Okay, thus it should look something like this. For example, packet 2 is lost. Then, if packet 2 times out, then you just need to reset packet 2. That's basically the goal of selective repeat. Okay, any questions? In a way, more efficient, but of course more complex to implement. Easy to see, but try code it out. Okay? Yeah. So you can see the algorithms later on in the book side. Then finally, let me just give a very quick discussion on TCP. Disclaimer, this might not be very complete, but it's sufficient for the tutorial first. Some more items, I'll add them in the tips later at the end. Okay? So TCP is what we call a connection-oriented, compared to UDP where it's connectionless. Okay? So here connection-oriented means that before you start sending data, you have to establish something called the TCP handshake. Anyone recalls what the TCP handshake is about? What do you do in a TCP handshake?
The scene acting.
Okay, scene acting. What is the scene acting?
So you send the scene, like the time sends the scene, and then an act is sent, and then there's a piggyback of the scene, and then finally a scene is sent.
Okay. Yeah, so basically TCP is like two-person talking, right? Two-person talking, they want to agree to start a communication, and that's when they want to agree, they have to set some terms, right? So say this is me, this is Michael, right? I will say, hey, let's use, say, sequence number 5. Okay, then Michael will say, okay. Then afterwards, Michael will also tell me that if he wants to communicate with me, we'll use sequence number 8. Then I'll say, okay. This is basically your TCP handshake. Okay, handshake, right? I tell you my name, you tell me your name, right? Okay, that's a handshake. However, we know that TCP is what we call the full duplex system. Thus, when we have a full duplex protocol, we can actually piggyback the data and the ACK. So this part, when Michael says okay, and he gives me his sequence number, it doesn't have to be separate communication. It can just be directly one way. Okay, so something like if I shake hands with someone, hi, I'm Jason. Then Michael will say to me, nice to meet you, Jason. I'm Michael. It's directly in one single conversation, right? It's not like nice to meet you, Jason. Pause 5 seconds. Hi, I'm Michael. Okay, so it's directly just one single thing. That's why we call this a three-way handshake, because you only need 1, 2, 3. The second one is just a combination of ACK and giving the sequence number of the other person. Okay? Then we know that TCP is reliable. To actually make this reliability, there's a whole chapter on Kurose and Ross 3.5. Please read this. And then we also have something called the flow control and congestion control, which is the key part of your TCP. So I want to highlight the difference of TCP with all the RDP protocols that we have seen thus far. When we are talking about TCP, the sequence number here is not the sequence number of the packet, but it represents the sequence number of the byte of data that you send. Say for example, if you send a file of like 10,000 bytes, if one packet contains, say for example, from 0 up to 100 bytes, then the sequence number here will be 0. This is the first packet. When you send the second packet, the sequence number here will be 100. So it will follow the byte number. Okay, but of course this will be added by the initial sequence. Okay, so that is your sequence number. For your ACK number, another thing to note, in TCP, ACK number of, for example, 95, this means that the next expected byte is 95. Everything up to 95 minus 1 has been received. You are expecting 95. That is the difference of your ACK here. In the past, for all the pipelining protocols, RDT protocols, when we say ACK, means everything up to that number has been received, right? Including that number. But for here, we are saying that everything up to that number minus 1 has been received. We are expecting this number. Okay? Make sure to know the difference. And yeah, this one you can check later on your own. This one I just copied from the lecture slide. However, the important thing to note here is that you use cumulative ACK for TCP. Sender keeps only one timer. And on the receiver side, it's actually more complex. So try to read this later on. Okay? Important thing to note is that the in-order segment here, there's a different protocol for TCP. I hope you all have read this or attended the lecture on this. No? Okay. Okay, then let's move on to the tutorial today. First one, is it possible for an application to enjoy reliable data transfer even when the application runs on UDP? Yes? No? Who says yes? No? No one? Okay. Why yes? Okay. Yeah, that is true. So basically, you can assume that your UDP is kind of the unreliable network layer, right? Then on your application layer, you can actually simulate the same thing, just redo whatever TCP does on the application layer. Then you will still enjoy reliable data. Okay, so every single mechanism that we implemented on TCP, you have to implement this now on the application layer. In short, you kind of like push the UDP down to like network layer level. Then on the application level, you have to redo all the mechanisms, checking and stuff. Redundant? Yes, that's why we use TCP. Okay, any questions? No? Okay. Yeah, basically you have to simulate your RDT-like protocols. Now, we want to show an example. If the communication channel between the sender and receiver can reorder messages, then protocol RDT 3.0 will not work correctly. Yeah, this one is actually more or less a challenging question, I guess. So, wait. How do we do this?
Is there like, can you not do this with a sequence number, or
Sorry?
does the sequence number not work in this scenario?
Yeah, how?
Okay, so assuming that the I'm using the wrong term. Client is sending the server a message, right?
Okay.
They pass the sequence number for each packet in sequential order. So then when like the receiver receives the packet, it can kind of like reorder the
Okay.
data itself. Unless I'm missing anything.
Yeah, but this is RDT 3.0, right? Stop and wait protocol. So not go back and not selective repeat. So recall that in RDT 3.0, how many bits of sequence number do we use?
1.
1. It's basically either a 0 or a 1, right? Once it passes through 1, it will go back to 0, go to 1, go to 0, go to 1. So is there any ways that that whole thing, as what Jerdine mentioned, will fail, the sequence number?
I think you can consider the case where you have, let's say for call 1, and then there's a timeout, and subsequently the message wasn't dropped, but then acknowledged message for call 1 wasn't dropped. It just took a longer time to reach the sender. So as the sender sends out a new 1 in that time frame, it got acknowledged by the previous not acknowledged 1 during the timeout.
Okay, so can you repeat again from the start?
So suppose the sender sent out a message 1.
Let's call this 0
Of
for 0.
Sure. Then in that process, right, there's a timeout because
Okay.
the acknowledge did not reach back the sender. And because of that, they send another packet 0. And in the process, he receives the acknowledged 0. No, sorry. Yeah, acknowledged 0.
Okay.
And they send out 1, they acknowledge 1, they send out another 0, and at that point, the first acknowledge from the 0 at that time reached the sender. Yes.
Something like this.
Yeah. So it crosses 2 of the cycles. So you reorder the.
Yeah. This one makes sense. Yeah, this one makes sense. But actually, I can show you later on that something similar to this But we can actually have a real problem for this. Okay, so this one actually you will see that it will go back to 1, right? So on the other side, this will just receive either 0 or 1, right? So it should be a bit okay, I guess. So here, let's see. Thank you very much, Jason. Yeah, so the same example actually. First one, sender will send packet 0. Okay, thus now receiver will ACK 0. But we assume that this ACK happens to be late. Exactly Jason's point. Okay, so up to this ACK 0 will come late. There will be a timeout event such that this will read transmit packet 0. Okay? But here what happens is suddenly your ACK 0 comes. Once your ACK 0 comes, this will send packet 1, right? Because it will assume that this packet 0 has been ACK. But in fact, this was the original ACK. Now, once this sends packet 1 will receive ACK 1, then this will send 0. Okay? This is lost. However, you will see that after this packet 1, this 0 will come in. But this 0 was the original one as the same as in the initial, right? So here, the receiver does not know whether this is actually the old packet 0 or the new packet 0. This is where the sequence number breaks. Okay? Any questions thus far? So because of the sequence number and also because of the timeout, this event might occur. Had there not been timeout, right? Had there you just wait for the ACK to come, then it will happen. But the ACK may never come and you might just start waiting. Okay?
But sequence number is like the 1, 2, 3, 4, 5, 1. Then what are they?
Okay. So in the case that 1, 2, 3, 4, 5, that's actually the next question. How do we how do we guard against duplicate packets? That's actually the next question. You have an answer? Okay, just now you mentioned 1, 2, 3, 4, 5. That's actually one way to guard against duplicate packets. Just now, because of just two sequence numbers, right, 0 and 1, then this event might occur. Had this been something like 0, then this will be 1, then this should be something like 2, right? Because ACK 1 is received, right? So this should be 2. Then if this happens, then this should not occur, right? Because on the receiver side, you know that if 0 happens, but the next one I'm expecting is 2, right? So this should not happen. Okay? So that is one way. What are the other ways?
You mentioned the lecture, so as you set out packet 0, you will only wait for acknowledge 0 to respond. And if in that case, acknowledge 1, wait, I think there's a
I think it's similar to just now, right? We have a timeout. Okay, so yeah. Basically, the approach that we use is that we don't want to reuse the sequence number. Okay, as for just now, what's your name? Xavier. Yeah, as what Xavier mentioned, we want to kind of increase the range of the sequence numbers. That is why you will see that in TCP, we use quite a large sequence number. The sequence number in TCP is actually 32 bits. Thus, we try to ensure that as much as possible, we don't reuse the same sequence number. Okay? You can try to see when we actually exhaust the sequence number of TCP. I think that is like a next tutorial question or something. Yeah. Then the second one is we kind of put another safeguard. That is, if a packet has been in the network for too long, it will be discarded. So we always include a TTL in the packet headers. That is actually done by the network layer. So in the IP, there's a TTL, such that whenever there's a network node who checks this packet, if this packet has already been too long, whoever in the network can just discard this on behalf. Because you will see in future lessons, when we discuss about routing protocols, it might be possible that a packet, right, if it goes through one router to the second router, to the third router, to the fourth router, back to the first router, this will go in an infinite loop. It might be possible. Thus, that is why you have to ensure that in this case, just resend the packet. Okay, the old packet can just be discarded. This will ensure that the initial ACK 0 that is too long, this will be dead by that time. Okay, any questions? Because if this is not implemented, then even a large sequence number is used, there might still be a very slight chance that it can still go back, right? Because remember, TCP is for bits. Yes, TCP is for the bytes. Okay? So if you exceed 2 raised to 32 bytes, then this might be reused, right? Okay, so this TTL is the way that we can ensure it will just live in the network for some time. Okay. Now, host A sends data segments to B using a reliable transport protocol. Then we assume that the timeout are sufficiently large such that all data segments and their corresponding ACKs can be received if not lost. Okay. Thus, we assume here that premature timeout will not occur. So suppose that host A sends 5 data segments to B and the second data segment is lost. Further, we suppose that retransmission is always successful. Anyone knows what this means? This means that when you resend any other packet, this will not be lost. Okay, that is what the line means. So how many segments has A sent in total? How many ACKs has B sent in total if GBN or SR protocol is used? Anyone?
For A is 9, because at the start you try to send the first 5. After the second one is long, so it transmit everything from 5.
Okay.
Then for B, the 8. The first one, after that it, then 5.
Okay. Yeah, this should be correct for GBN. Thank you. Then SR. And what's your name? Lyndon. Okay. Thanks, Lyndon. How about SR? Anyone?
6 packets and 5 acknowledgement.
Okay. 6 packets plus 5 ACKs, right? Because one of the ACKs are lost because of the packet. Yeah. Okay. Thanks. Your name? Chanyang. Okay. Okay. So yeah, this is for go back N. We see that packet 2 is lost here. 1, 3, 4, and 5 is received. So there are 4 ACKs that are sent by B, right? Then afterwards, because this is lost, all this ACK1, so after the timeout for the last unacknowledged packet, we are going to resend the window from 2 all the way up. Okay, so this will be 2, 3, 4, 5. Thus, this will send out 9 packets and there are 8 ACKs after this. Okay? For selective repeat, since we buffer these out of order packets, so after this timeout, you just resend packet 2. Okay? That is when SR might actually be more efficient. Any questions? Clear? Okay. Now, question 5. Now is more on TCP side. So suppose that host A sends 2 TCP segments back to host B. First segment has sequence number 65. Second one has sequence number 92. How much data is in the first segment? How is it 27? Exactly. Okay. So remember that the 65 here represents the first byte in that packet, right? Byte number 65. Then in the second packet, it's byte number 92. So we want to consider from 65 up to 91, how many bytes are there? Okay, so just 92 minus 65. Okay, so that gives you 27 bytes of data. Okay, now the fun part. Suppose that the first segment is lost, but second segment arrives at B. In the acknowledgement that host B sends to host A, what is the ACK number? $65. Why is that so? Because 65 is the next byte that B expects. Okay? First packet has not received, right? So B still expects 65 to receive first. So it will send ACK 65. Okay? That is when TCP is different. Any questions? Of course, this one assumes that prior to this, either no connection has occurred or there are connections done, but it has all been received because there are those underlying assumptions. Okay. Okay, and finally here, we consider transferring an enormous file of L bytes from A to B. Assume that an MSS of 512 bytes. What is an MSS? Maximum segment size. Okay. So what is the maximum value of L such that TCP sequence number are not exhausted? This is the one I mentioned just now. This one? Why is it 2 to the power of 32? Okay. So, yeah. Since TCP sequence number doesn't increase by 1 with each TCP segment, thus we just need 2 raised to 32 bytes. It's not 2 raised to 32 times the MSS, okay? Yeah, what's your name just now? Alina, okay. Question? Why is it not minus 1? 2 to the power of 32 minus 1 is the maximum sequence number. But if you consider 2 to the power of 32 minus 1 plus the one sequence number for 0, that is 2 to the power of 32 bytes, right? Yeah. So the range is from 0 to 2 to the power of 32 minus 1, which is 2 to the power of 32 numbers. Okay? Okay. So yeah, we found that the L is 2 to the power of 32 bytes. How long does it take to transmit the file? Which assume that 64 bytes of transport network and link headers are added. Then we send it over a 155 megabit per second link. Okay, so let's see how we do this. We have a file size 2 raised to 32 bytes. Okay, how many packets can we form here? We have to now adhere to the MSS. Our MSS is 512 bytes, right? So we have to split them into chunks of 512 bytes each. Okay, 512, 512, 512 all the way. Each of the packet here now will have to be added by the headers, which includes your TCP header, IP header, and all those. Okay, so additional overhead is your 64 bytes. Thus, this will account for number of packets is this 8 million packets. You multiply this by 64 bytes. This is additional data overhead. So in total, 2 to the power of 32 plus this additional overhead, this will give you this number bytes. Okay. So this number bytes, just count the transmission delay. Just divide this up. Okay. Since these are bytes, convert them to bits first. Don't forget. Times 8 divided by 155 times 10 raised to 6. This will give you about 250 seconds. Okay. So fun fact, 2 raised to 32 is about 4 gigabytes. Okay. So this means that for 4 gigabytes, you send it over 155 megabit per second, takes you about 6 minutes. Okay, any questions? Okay, so if no questions, this part I'll just skip first. If you're interested, there's a recording for this I'll share later. But before that, quite happy that we ended this 30 minutes. If y'all have anything to do after this, feel free to leave. Otherwise, I'll share some of the tips basically for midterms. My tips is only one. Read the question carefully. That's my actual only tip. Okay? Why do I say read the question carefully? As I mentioned last time, there are questions that might write microseconds instead of milliseconds, bits instead of bytes, bytes instead of bits. Okay? So make sure to kind of read the question carefully. If possible, try to underline some stuff. Okay? Second thing is, I think the midterm is open book, is it? No? It's open book, right? Okay. Print out everything. I am being honest, print out everything. Because the lecturer will only include questions that are present on the lecture, right? But there might be some times that you don't know whether something exists or not. For example, later on I'll show one item that you might not know it exists. Okay? Actually, I haven't checked with the exercise this sem, but last sem it exists. So what kind of questions there are? Let me show you some kind of a misconception that we have okay, throughout the past midterms. I think that might help actually. So instead of me telling you all the misconceptions, I know that you might not be understanding it that well. So what if we share this in a fun way? Yeah. So I prepared a very quickie Kahoot quiz. Prepare your phones, Kahoot.it, you know the drill. Yeah, can join the link here. I compiled about 18 questions of the common misconceptions I think will occur on the midterms. How come no audio? Oi! Oi! Who among you Indonesians for this? I don't want to go to jail, guys. Please let me know if you can join. Anyone still joining? Joined already? Okay? Okay, then let's start the quiz. Just full screen this. I think the first part is easy. Internet protocol stack consists of how many layers? Yeah, should be 5 layers. So the previous item that I showed you, it is actually a different stack. It's called an OSI model. Same stack, but it actually expands more. So for the context of the module, we introduce IP stack in terms of 5 layers, although there are other frameworks. Okay? Clear? Let's see who wins. Where's Prabowo? Hey, what does UDP stand for? Hey, I taught you well, yes. So last time when I did this quiz, right, the unreliable thing was actually higher. I taught you well, yes. Happy. Okay. Oh, Nathan goes up. Karen also. After receiving a data packet, TCP sends ACK96. What is the next byte of in-order data expected? Okay, so we have a split kind of group between 96 and 97. I don't know who chooses Jason. Maybe it's Jason. I don't know. But anyways, remember that for TCP, it's your ACK number represents the next byte you expect. So if it is ACK 96, then you expect the next packet to have sequence number 96 to receive. Okay? Next byte expected. It is different from all your RDT and pipelining protocols. Okay? Make sure you know this. Wow, some people fall down. I'm sad. Which of the following statements is false? I should have worn my Cookie Monster shirt today. Do you see it in your phone? I think the phone has answers also, right? No.
No.
Never mind. Y'all want to come closer to the front here, please? We have like, what, 6 empty seats in front. Those in the back can move forward. Standing also can. Okay, kind of 6 to 8. Okay, so let's discuss this. Both HTTP 1.0 and 1.1 are designed as stateless protocols. This one should be true because in your HTTP, right, you should assume that whatever request you are handling depends only on what you're requesting. Okay, should not depend on past data unless you append some data or something like that. Okay, of course there are some other ways that as backend developers you want to kind of make it stateful, but in the original case it was actually designed as stateless. Okay, so if you want to get google.com, you get it 5 times, it should return the same thing. That's basically your HTTP. Should not depend on any state. Cookie can be configured to expire after a certain time. I think this one is true, I think. Quite obvious. Cookie can build stateful interaction between client and server. This one also true. That is why whenever you have cookies, right? Today you search something on Shopee. Something what you search? Fried rice cooker. Okay? You search rice cooker on Shopee. Tomorrow you will see an ad on Amazon about rice cooker. The next day you go to Shopee, right? Your FYP page is always rice cooker, right? So that is how cookies actually build some kind of a state where you remember things. Now the last one. This one is false because it is not stored in the database of the server, but rather it is stored in the client. Your browser, your local machine, it will store the cookies. So whenever you actually create you actually request, right, then the cookie will be sent again. So it will be stored in your browser. The logic here is, if you want to clear your cookies, it's possible on the browser. It doesn't have to contact the server, right? You remove Google Chrome, everything will be deleted. Okay? Okay. Oh, I forgot to see the leaderboard. What is the checksum of 1001, 001? Count now. Don't be lazy. Hey, where's my Zoom? Where is it? What happened? Everyone knows how to count this? Anyone can mention what the problem is? Okay. For this one, actually, I want to share you a bit of a trick lah. Okay, so let me just unshare my screen. Yeah, let me go to this Zoom. So what do you do when you see this kind of question in your midterm? You count this, right? Okay, let me show you a very quick trick here. So let me, okay. Why am I showing my face? Switch camera. So I want to count this checksum. Okay, that means if I sum this up, if I get the sum, I can just flip everything, right? Here's how you can do it. You can use your calculator actually to compute this. Okay, everyone has this kind of calculator or any class V's more advanced item, then can compute it. So I will show you how. First one, you will see here that there's a mode, right? If you click on the mode, then you will see like different options. There's a base n over here. This base n is actually the one thing that allows you to convert between decimal, binary, hexadecimal, and octal numbers. So I go to 4. This is a base n number, right? Okay. Then I will have to convert my mode here to binary. So this is decimal, this is binary. This is decimal, this is binary, right? So I convert to binary first, then I just need to sum it up. 10010011 plus, okay, my screen broke. 100110001. Okay. I don't know why, but oh well. Unfortunate. But anyways, I'll just show it live lah. Something like this. Okay, you enter the numbers. After you equal sign, this will give you the binary sum directly. Okay? It will tell you that there are 9 bits here. Oh my god. Okay, it will tell you that there are 9 bits because there's a carry. All you need to do is just move the carry one, right? Then problem solved. Okay? So in the exams, if in the case that you have this kind of questions, all you need to do is to just use your calculator lah. Don't spend too much time on this item. Okay? Yeah. Also, I'll just share a bit of a trick also. Wait, where's my video? It's gone. Anyways. So with this, you can actually convert decimal to binary numbers also. So how do you do that? Say you want to convert a number 192 to binary. Okay? Then the first thing you do, you go to mode, click on base n, you enter the number first, then it will show decimal 192. Okay? Once you're done, just click on this binary number, it will convert this to binary directly. This will be helpful for today's lecture where you will learn about IP addresses. Because on the midterm, it might be tested how to convert a binary number to IP address. Then you use this one. Okay? Cheat trick. I shall introduce this today because no time for me to introduce next week. Okay. Okay, some people got it wrong. Okay, let's move on. True or false? Maximum segment size is inclusive of the TCP header. God. Oh, you see my quota now. Actually, I provided the cheat sheet here in a photo, but it's not loading. Oh well. Unfortunate, guys. Okay, so this is false. Your MSS is actually not inclusive of the TCP header. Okay? MSS is just how much data can the application layer send. Okay? So how do you visualize this? Actually, I will show the media here. Mark. You have your maximum transmission unit. This is basically determined by your link layer. MTU minus your IP header minus your TCP header, this will give you an MSS, which is how much application layer data can you send in one go. Okay? Questions? Okay, right? Whoa, lean goes up. Congrats. Which of the following fields are present in TCP but not UDP? I think this one is easy. Okay, so ACK number is not present in UDP because UDP does not need to acknowledge. It's a wait only, right? I send you, I don't care if it receives or not, you don't have to reply me that you received. So ACK is not present in your UDP. PTL is actually not part of TCP or UDP. This is part of your network layer. Okay? Questions? Source port of course have to be present in both. Checksum also have to be present in both because you have to check for corruption. Okay? Yeah. This is why I made this quiz because it's a common misconception. Okay? Selective repeat protocol stores timers for each un-ACK packet, true or false. Easy lah, this one. Oh, we have some time. It's fine, next class is my class anyway. So. Okay, this one's quite easy. I don't need to explain now. Okay, next. DHCP runs over something DNS runs. Oh, never mind. DHCP has not been discussed, right? Forget this. You can guess, you can guess. So DHCP is basically when a host comes in, how do you get the IP address? It's a protocol to get the IP address when the host just enters the network. So you can get from there. Okay. Okay, when you want to get an IP address, right, technically you don't need reliability also. If the person doesn't respond, I just resend. So it doesn't have to be a reliable item. Unless, for example, you want to send an email or something like that when you need reliability. Okay, so the key part here is whenever you don't need reliability, no need to implement much item. So both of these should be UDP. Okay? Okay, only Nathan got it correct. Congrats. Double points. Most network protocols are specified in RFCs. What does RFC stand for? So TCP is part of RFC 793 by the International Engineering Task Force. So this RFC stands for something. That's a hint already. Okay, great job. So RFC is request for comments. It's basically a proposal. Okay, it's lucky because I show the media. Probably if not the media, maybe some people would choose this one. Yeah. So a hint, extra knowledge. This was the midterm last sem. Everyone chose request for communication. Because there's no media, right? It's just the text. Okay. Yeah, so RFC is request for comments based on the Internet Engineering Task Force. Okay. In socket programming, sock diagram is used for what socket? Sock stream is used for what socket? For those who have looked through the codes, you should know. I give a hint there also. So this photo I took from internet. I don't know who this face is. Don't ask me who. Okay. So just now you see that in the media it says connectionless. So sock diagram is for UDP, sock stream is for TCP. Okay. Okay. Oh, Prabowo goes up. Okay, let's go Prabowo. Okay, checksum is computed for and attached to yada yada yada. For RDP 3.0. Those at the back, you may want to go to front, it's fine. Oh! Okay, let's discuss this. DT 3.0, is there NAK? No. So 3 and 4 is wrong. Okay? Is it first one or second one? Can ACK packets be corrupted? Yes, that's why it's the first one. Easy, right? Okay? Because your ACK and your data can be corrupted, so both of them should have the checksum. By default, DNS server listens to which port number? How many questions do I have left? Oh, shucks. Okay. 53 is for DNS, 22 is a random number, 80 is for a TCP port, usually for HTTP. 8080 is a, I think this is a Django localhost. Okay. Oh, sorry, this is a Vue localhost. Okay. Yeah, so it should be 53. Check your lecture notes later on. Double points. Which of the following is a wrong implementation of TCP? This one is fun. So long, Just decide, So it's challenging actually. Hey Brian, if you need to leave, can leave also. It's fine. Pretty sure majority will not get this correct. Oh, majority got it correct. This is actually a challenging problem. 3 and 4, I think this one obviously correct. Okay, 3 and 4 has been discussed. The problem is between your 1 and 2. Apparently, if you look through the fine print of TCP, in the book, it specifies that what does a host do when it receives out of order packets. There are two things that you can do. It is left to the programmers to implement it. Okay, so TCP does not provide it. So first one is either you immediately discard, or second one is if you buffer them out. Okay, so both of them are acceptable. Why was the second option the false option? Because TCP uses cumulative ACK. If it ACKs individual one, then there is a wrong implementation. But if you directly discard, this is also correct implementation. That is why please read your Kurose and Rose chapter 3.5. This was a midterm question, by the way. I'm pretty sure this is not covered in the lecture. Okay. Now the double points. A sends 5 packets to B using TCP. Within 100 milliseconds, B receives 5 in-order packets. How many ACKs will it send? Please enter your options early so we can skip this part. I put this at 60 seconds, so many. It's obviously 1, 3, or 5, right? How hard is it? I think while we do this, right, let's discuss. Can it be 5? Actually, this part actually comes in handy. The within 100 millisecond duration. Okay, we'll see the answer. If you see a double point question, you know that it's actually a hard question. So if you recall on the lecture, on the tutorial slide just now, I did highlight part of the TCP receiver that's important, right? This is your TCP implementation. Wait. These two are about in-order segments. if some in-order segment arrives, but there's no outstanding segment, then this will have a delayed ACK, as what the lecturer mentioned, right? It will wait up to 500 milliseconds for arrival of the next in-order segment. But this 500 millisecond wait is not cumulative in a sense. So it will wait up to 500 milliseconds for the next item to arrive. Once this next item arrives, it will ACK both these packets. It doesn't wait for the third item to arrive again. That is the difference of your cumulative ACK in normal cumulative ACK and this item. So cumulative ACK does not mean that you wait for all packets to arrive, but it means that any packet that is ACK to that point, all of them before that has already been ACK. That is your cumulative mean. It does not mean that it waits. Okay? But for this case, your TCP, so if B receives like within 100 milliseconds, receive 5 items, right? First one, delay. Then the next one comes, this one is like less than 100 milliseconds. Since it's within the 500 ms, both of them will be ACK. One ACK. Okay? First one come in, delay. Second one comes, both of them will be ACK. Finally, the last one come, will be delayed 500 ms, but since no one comes again, ACK. So 1, 2, 3 ACKs. Okay? Questions? What is Jason's favorite color? If anyone finds this video, please don't tell me. Just because I wear green doesn't mean I like green. So, last sem, right, for this Kahoot, I actually wear all blue. Everyone just blue also. This tells me that everyone judges a book by a cover lah. Okay? Yeah. Ah, shucks. Player limit reach. Okay, anyways. Random luck. Let's pick any. I still have one more question after this. Okay, just random. This tells you that for your midterms you need luck also. Go pray, go pray. You want to go to church this Sunday, please go. You want to go to temple this Sunday? No, this Saturday, Chap Gome. Go. Okay, last week's discussion question. This is a point for those who actually do the questions. I eliminated the obvious answer, A should be false lah. Because of course it can be corrupted, right? So checksum will be needed. But which other option is correct? People didn't do their homework. So apparently in my other tutorial class after this, they actually discuss it in the group lah. So I'm predicting it should be much more. Okay, so that concludes the Kahoot. But before that, let's discuss what the last week's question was. Okay, so this was the bonus question that I provided last week. Option A, true or false? False, right? Because your data can be corrupted. Option B. B should be false because sequence number has two reasons. First one is for your reordering, in the case of backend and selective repeat. The second one is to detect duplicates, because or else you don't know whether this packet was a previous one or the new one. Okay? Thus, since your feedback packets can be lost, your ACK can be lost, right? So duplicate items might exist. Thus, the sequence number is needed. Okay? Third one, setting a timer is for like packet loss, right? Since there's big packet loss. However, setting a timer properly is basically to handle premature timeout. That is what if you suddenly went a bit slower lah. So you kind of like want to set it properly so that if it is successful, it should come. Okay? So it is to mitigate premature timeout, but it is not to mitigate the chances that receiver may receive duplicate packets lah. Something like that. Okay? So in the case that the feedback packets is lost, ACK is lost, then duplicate packets may exist. So the timer does not have anything to do with it. So this is actually the hard option. Option D, yeah, if this is changed as the feedback packet may never be lost or corrupted, then C will be true. Okay? Because it will always arrive, right? So it should be correct. Then Last one, D. D is false also. Because since we assume that data packets are lost, then reliable protocol will have to implement a timer to retransmit. Thus, if say that your receiver does not acknowledge a duplicate packet, it will go here duplicate, right? Doesn't acknowledge, timeout, send again, does not acknowledge, timeout, send again, right? This will just be a cycle. Okay? So thus the option should be E. This is the hardest question in my midterm last time when I did it. Okay? So with that, then I guess that should be enough tips, I guess. Address some misconceptions. If possible, please give your Kurose and Ross a read. Otherwise, then that is it for the tutorial. Before that, let's see the leaderboard. Hey, Galen. Hey, for those who win, top 3, please come forward. I have prizes. Yeah. And for those who haven't marked the attendance, please let me know. Okay, for those who are here, can pick one pocky and choose one attendance. Okay. Yeah. Eh, names? Moon Hui. Okay. Thank you. Alina. Xavier. Chen Xun. Nathan. Oh yeah. Thanks. Okay. Sorry, is Amos here? Xiao, Yi, Chan Yang is here just now. Yeah.
For sure. You say that seven is equal to 6. Then the other one is 92. How much data is in the first one? Why is it 92 minus 65?
Okay, so let's say let me take a simple number. Say the first packet has a sequence number of 2. Second packet has a sequence number of 4. This means that the first packet contains sequence number 2 and 3, right? So how many bits? How many bytes?
Oh, sequence number not. Oh, this is acknowledgement number.
Even the acknowledgement number also the same. Say if this is acknowledgement number, when this is received, it will send ACK 4, right?
Yes.
Say next one receive, this will send ACK 6. So what is the number of data in the second packet? Then there is a 6 minus 4, right? Also the same thing.
This is the But now that the number is at the front, you just in between.
Yes. So if you visualize with a small example, you'll see it too.
Also, for this question, the 100 millisecond one is derived from deduction. This question, the 3.
No, the 100 milliseconds is actually so that it will not exceed this 500 millisecond limit. That's basically saying that the cumulative ACK should work.
But you say the cumulative ACK is the 500 millisecond is after you wait 500 seconds, you will send 1, right?
After 5, so first packet comes, right? It will take 500 milliseconds. If anything comes within this 500, both of them will be ACK as one.
Shot.
If no one comes, then it will just ACK itself.
Yep, correct. So, but this when you have one packet, because you don't really know what's the transmission time for a single packet. Right now,
you don't care about the transmission time.
Right now, it's assuming 2 packets come in, then 1 combined acknowledgement.
Yeah.
How do you know is it 2 packets or 3 packets?
That's why we say that within this 100 ms, right? We don't care of whoever arrives. Can be random also. But since it's 100 ms, it will be definitely less than 500 ms, right? So this should hold.
Bruh.
But the option was 1, 3, and 5, right? So how do you make the deduction? Is it a deduction or is it
How deduction?
because it cannot be 5 because we know that it's gonna be a cumulative acknowledgement, right? And it can't be 1 because
5 is possible if all of them exceed 500 ms.
1 also possible.
Because cumulative, that's the misconception, right? Cumulative ACK does not mean that you wait everything to come then you send. But cumulative ACK means that if I have ACK number of something, means everything after this will already been received, so I don't have to bother about the previous ones. So cumulative does not mean I look forward, but it means I look backward, all of them are sent, are received. That's a misconception, basically.
Thank you so much.
Yeah. Hi. Okay, let's start with a very quick attendance. You have seen a spoiler there. Okay, Abi here. Okay, Benedict. Kui. Chi Kwan. Derek, Edmund, here, He Jin, no, Ivor, James, Gerald, Jody here, oh yeah, Jun Feng here, Kiwei, Lauren, Shi Hui, Sidan, oh, Stefan, no, Tom, Xavier Lee, Xavier O, Yiming, Yongrong. Okay, let's start today's class. A bit delayed, sorry, but oh my, I forgot.